Chapter 15 continues our exploration of chemical equilibrium. In this chapter, we'll apply the equilibrium concepts we've learned in chapters 13 and 14 to reactions involving sparingly soluble solids and complex ion formation. We will also introduce the concepts and problem-solving strategies necessary for solving systems of multiple equilibria. Section 15.1 covers precipitation and dilution. In this section, we will look at the equilibrium expressions and equilibrium constant values for reactions of sparingly soluble ionic salts dissolving in water. We will also apply concepts like Le Chatelier's principle to make predictions about shifts in equilibrium positions and introduce the topic of qualitative analysis. Before watching this video, make sure that you have completed the reading guides for section 15.1 from the textbook. Have your copy of the Chapter 15 handouts ready to take notes on as we work through this section. First, we need to start off with some definitions. A saturated solution is a solution that contains the maximum amount of dissolved species. For any given solid, there will be a set amount that can dissolve in a given amount of solute at a given temperature. The beaker below shows a saturated solution. The liquid on top is a solution containing the dissolved solid. In this case, there is extra solid in the beaker that can't dissolve because the liquid part already contains the maximum amount that it can hold. Solubility is an equilibrium system. The beaker on the right shows that individual particles are continually dissolving and recrystallizing even though the net amounts of solid or dissolved species aren't changing. An unsaturated solution is a solution that contains less than the maximum amount of dissolved solids. For example, when you start to add sugar to water, it all dissolves and you have an unsaturated solution because additional sugar can still dissolve. A supersaturated solution contains more than the maximum amount of dissolved solid and is thermodynamically unstable. I've posted a cool video of what happens to a supersaturated solution when a small seed crystal is added. Molar solubility is the concentration of solute in a saturated solution and has units of moles per liter. We also sometimes use the word solubility to indicate the concentration of solute in a saturated solution in units of grams per liter. Notice that both of these numbers describe saturated solutions and indicate the maximum amount of a particular solid that will dissolve at that temperature. In this chapter, we will be focusing on the solubility of sparingly soluble ionic compounds. A generic equation showing the relevant chemical reactions is shown here. We will define a new type of equilibrium constant, or K value, for these reactions, and we will call it KSP. KSP is the equilibrium constant for the specific reaction of the dissolution of an ionic compound. Let's start by looking at the example of magnesium hydroxide. Magnesium hydroxide is pretty insoluble. It has a molar solubility of 3.72 times 10 to the minus 5 moles of magnesium hydroxide per liter of solution. This equates to a gram solubility of 2.17 times 10 to the minus 3 grams of magnesium hydroxide per liter, and a KSP value of 2.06 times 10 to the minus 13. Notice that these quantities are all related to each other, but they are not identical. Let's write the reaction for the dissolution of magnesium hydroxide solid in water. When magnesium hydroxide solid is added to a beaker of water, some of it will dissociate to form magnesium 2+ ions and hydroxide ions. We can write an equilibrium constant for this equation, following all the same rules that we've learned before. The equilibrium constant is equal to the concentrations of the products divided by the concentrations of the reactants. In this case, the KSP for this reaction is the concentration of magnesium 2+ ions times the concentration of hydroxide ions squared. Remember that pure solids don't appear in equilibrium constant expressions. The KSP of magnesium hydroxide is 2.06 times 10 to the minus 13, which is a pretty small number, indicating that magnesium hydroxide is not very soluble at all. We can set up ice tables for dissolution reactions to determine the molar solubility from the KSP value and vice versa. Let's show the ice table for this reaction. In our initial row, we don't put a concentration in for magnesium hydroxide solid because it's a solid species. We'll assume that the amount of magnesium ions and hydroxide ions in the solution are initially 0. Our change row will follow the conventions that we've used before. Since the reaction will proceed in the forward direction, we'll use minus S for the reactant and plus S and plus 2S for magnesium 2+ and hydroxide respectively. We're using S in this case to indicate solubility, but we could use X's as well. It's the same. So at equilibrium, we should have S concentration or S molarity of magnesium 2+ ions, and the concentration of hydroxide should be 2S. We can plug these equilibrium values into the KSP expression, combine terms, and solve for S, which will be the molar solubility. In this case, S will have a value of 3.72 times 10 to the minus 5 molar. S is the molar solubility. It's the moles of magnesium hydroxide that dissolved. S is also equal to the concentration of magnesium 2+ ions that will be in solution. But because of the 2 coefficient for hydroxide, the concentration of hydroxide ion solutions will be equal to 2S. We can take the molar solubility and convert it to a gram solubility by using the molar mass of magnesium hydroxide. This gives us the 2.1 times 10 to the minus 3 grams of magnesium hydroxide per liter that we saw above. Notice that we used the molar mass of the whole magnesium hydroxide because solubility is given in terms of the original solid. The KSP values for several salts are shown in the table. Actual solubility will depend on the value of KSP, which remember is temperature dependent, but also on several other complicating factors, all having to do with competing reactions or equilibria, such as the stepwise dissociation of ions, the formation of ion pairs, the pH of the solution, something called the common ion effect, which we'll explore, and complex ion formation. I think now is a good time to review the different K expressions that we've seen so far. I call these the special Ks. We've already seen that we have a definition for something called Ka. That's the equilibrium constant for the reaction of a weak acid in water. Kb is the equilibrium constant for the reaction of a weak base in water. Kw is the equilibrium constant for the very specific reaction of the self-ionization of water. And now we have a new one, Ksp, which is the equilibrium constant for the dissolution of a sparingly soluble ionic compound in water. Remember that each of these constants represents a number that corresponds to a very specific chemical reaction. So when we say something like the Ka of HF, for example, it isn't just about the HF. It means the equilibrium constant for the reaction of HF in water to form H+ and fluoride ions. Let's start by walking through some calculations for a few examples before having you work on similar group problems together. Question 1 asks us to write the chemical reactions corresponding to the solubility reactions of the following salts and to write their KSP expressions. The first one is silver sulfide. We need to know the formula for silver sulfide, and to do that we need to know the ions involved. Silver, when it's an ion, is always +1. Sulfide will be S2-. So the ionic compound formed from silver and sulfide is Ag2S. When this solid is added to water, some of the ions will dissolve, and we'll get 2 silver ions and the S2- ion. The KSP is always concentrations of products over reactants. In this case, we'll have the concentration of Ag+ squared, because of the coefficient, times the concentration of the sulfide ion. Again, because silver sulfide is a solid, this does not appear in our KSP expression. What about aluminum sulfate? Aluminum sulfate is an ionic compound. Aluminum will have a +3 charge. Sulfate we know is SO4 2-. So our solid will be Al2SO4 3. The solubility reaction will show this dissociating into 2 aluminum 3+ ions and 3 sulfate ions. Always remember that you have to show charges on any ionic species. The KSP expression, again, is the K for the reaction that we've shown, products over reactants. We'll have aluminum 3+ squared times the concentration of sulfate to the third. Let me just fix that up a little bit. Question 2 gives us the value for the KSP of lead 2 chloride. It has a value of 1.17 times 10 to the -5. We're asked to calculate the molar solubility and gram solubility of lead 2 chloride. So first we need to know the formula for lead 2 chloride. Since lead has a charge of +2 and chloride has a charge of -1, the formula for lead 2 chloride is PbCl2. What is the solubility reaction? Lead 2 chloride will dissociate into lead 2+ ions and 2 chloride ions. This is the reaction that goes with the KSP value, which is 1.17 times 10 to the -5, and is equal to the concentration of the lead ions times the concentration of chloride ions squared. The molar solubility asks how many moles of lead 2 chloride will dissolve per liter of solution. So we need to set up an ice table to find the equilibrium concentrations of the lead ions and the chloride ions. Again, for solids, we don't need to put in a value for concentration. We assume that we start with 0 lead and 0 chloride in solution. Our change will be -S plus S plus 2S. So at equilibrium, there should be S molar of the lead ions and 2s molar of the chloride ions. To solve for S, we need to use the KSP expression. Substituting in our values from our S table, we have S times 2s squared is 4s cubed, should be equal to 1.17 times 10 to the minus 5. We can solve this equation for S, and we get a value of 0.0143. Remember that S will be equal to the concentration of the lead 2+ ions in units of molarity, and will also be equal to the molar solubility. Because it's the moles of lead 2 chloride that actually dissolved. If we wanted to find the concentration of chloride ions, that would be equal to 2s, or 0.0826 molar. We were also asked to find the gram solubility of lead 2 chloride. We can get the gram solubility from the molar solubility. So we had 0.0143 moles of lead 2 chloride per liter of solution as our molar solubility. But 1 mole of lead 2 chloride weighs 278.09 grams. So that means 3.98 grams of lead 2 chloride would dissolve in a liter of solution. In question 3, we're given the gram solubility of strontium fluoride to be 7.3 times 10 to the minus 2 grams per liter, and asked to calculate the value of the KSP. This is essentially the reverse of the previous problem. Again, we need to start by writing the equation for the dissolution of strontium fluoride. And we can set up the KSP expression. It's going to be equal to the concentration of strontium 2+ ions times the concentration of fluoride ions squared. So if we want to determine the value of KSP, we'll need to know these concentrations. Remember that these represent the maximum concentrations in solution in equilibrium with the solid. What are those concentrations? Well, we were told that the gram solubility of strontium fluoride is 7.3 times 10 to the minus 2 grams, and again, that's the grams of the solid strontium fluoride per liter of solution. We can use the molar mass of strontium fluoride to figure out how many moles this would be. See if I can clean that up a little bit. The grams of strontium fluoride will cancel, and we get the molar solubility to be 5.81 times 10 to the minus 4 molar. What does that represent? Again, that's the molar solubility. Or our S value. Remember that KSP is going to be equal to the equilibrium concentration of the strontium ion times the equilibrium concentration of the fluoride ion squared. The strontium ion will be S, fluoride will be 2S, and we have to square that. So KSP is going to be equal to 4S cubed. And this is our value of S. So plugging that in, gives a KSP value in this case of 7.84 times 10 to the minus 10. Now that we've done a few examples, you should be ready to do group problems 1 through 5 in the group packet. The next video will look at predicting precipitation.